Okay, so the next example is again a very classical example. Is a farmer enclosing a region that he wants to use as a fence. So we have a farmer has 2,400 feet of fencing, so this is going to be important, and wants to fence off a rectangular field. Okay, this is also going to be important. That borders a straight river. He needs no fencing along the river. This is also important. What are the dimensions of the field? So we're looking for dimensions of the field that has largest area. So this is also important. Okay, so this is the key part of the problem is we know that we have 2,400 feet of fencing, and we're trying to make a rectangular field. Okay, so this 2,400 feet of fencing is going to represent the perimeter of the field that he's making. So if we think about it, here's the river. A little water here. And we don't need any fencing along here. So we're making this rectangular field like this. Okay? So the sum of these three lengths of fencing is the 2,400, which is exactly the perimeter of this shape right here. So if we label this Y, we know that this is also Y, since it has to be a rectangle, and we're going to call this X. So the first thing that this problem is telling us is that the perimeter, which is, in this case, Y plus X plus Y, if you add all these up, which, if you simplify this is 2Y plus X, that's going to be equal to 2,400. So this is the first important equation that we get out of this information, is that 2Y plus X is 2,400. And that basically has to do with the perimeter. And you may be saying, okay, well, this has nothing to do with the area. Why are you caring about the perimeter? So we'll see in a second why this is important. Okay? Now, we want to maximize the area. So what is the area of this rectangle? Well, it's the product of this leg with this leg, right? X times Y gives you this area, base times height. So the thing we're actually trying to maximize is the area. But unfortunately, this is going to be a function of two variables, two things that can actually change. So the area as a function of two variables is actually X times Y. And this is where knowing this is going to help us. Because right now, this is the function that we want to maximize, but in order to maximize it, we need to take its derivative, to see where the critical numbers are. But the problem is we don't know how to take the derivative of a two-variable function. So this is what we're going to use here. So let me recopy it here real quick and erase it down there for you guys. Okay. Now the easiest thing would be to just get X in terms of Y, because you don't want to solve for Y. That will require some division by 2 and stuff. So what we can do is, if you subtract 2Y from both sides, you get that X is going to be 2,400 minus 2Y. What we're going to do is we're going to stick this X in here, and for the X in there. This is going to be replaced. Make this substitution. Okay, so now our new and improved area equation, just as a function of the variable Y, will be 2,400 minus Y, 2Y, sorry. So So 2400 minus 2y, that's what x was, and then times the y that was already just floating out there to begin with. And now we're in business because our function is in terms of one variable, and this is kind of the thing that's going to happen a lot with optimization problems, is that you'll use one piece of information to reduce your equation of two variables into just a function of one variable. Okay, so now we maximize this the same way that we normally maximize functions. We take the derivative, find the critical number, and proceed. So first let's simplify this a little bit. Distribute the y. You get this minus 2y squared, and now we'll take the derivative. So this will just be 2400 minus 4y. Okay? Now, again, from the first example, we know that there's two cases to consider. So case one is a prime does not exist. Okay? But if you look at a prime, it's a very nice function. There's no division in here, there are no square roots, so there's nowhere that we can make this function mess up. All of the inputs y, when we replace y with this thing, will always give us a nice number. So this case is kind of out. So the only case that's going to give us a critical number is a prime of y equals 0, is where we get the derivative equals 0. And to solve for this, we just set our function equal to 0. So take 0 equals our function, the derivative function, and just solve for y. So you add 4y to both sides, and you get 4y is 2400 divided by 4, and you get that y is 600 feet. Okay? Now, in this context, it may be like clear that, okay, this has to be the maximum, but we still need to justify this. And remember, the way that we justify it is using the first derivative test. So again, we're going to make a nice little table and check the sign of the first derivative before and after 600. Okay, so here is 600, and here is a prime of y. Okay. Now, this is the derivative function. So, as you can see, again, like in the last problem with the turkey, you can't have a negative length. So, the domain is 0, so 0 feet of fencing for this, for the vertical leg, up to, you know, whatever. But 0 is where we have to stop. And so 0 is a nice number to actually pick here. It's a number before 600. So if we find a prime of 0, that's just going to be 2400 minus 4 times 0, which is positive. Like this is the function. So right, it's 2400, which is positive, okay? So this is positive, and now pick a number larger than 600, maybe let's say 1,000. So 2400 minus 4 times 1,000. Well, this will become 4,000, right? 2400 minus 4,000 is less than 0, so negative here. And so, yes, we have justified that this is actually the only maximum. Just like in the previous problem, we know that the function now, again, this is not exactly what the function looks like, but the area as a function of y looks something like this. It's increasing, and then suddenly it's decreasing, always. And at 600 is where it changed. So the function was always increasing, and then right after 600 it's always decreasing. Meaning this has to be the global maximum. It is the only case. There is no other possible maximum values. So what we conclude is So this dimension, the dimension of this leg, 600 feet, is what gives the maximal area. So all we have to do now is find the dimension of the other leg, which we call x, the width. So remember, this is what we had. This was y and this was x. So we found y is 600, and now we just need this x. But we can use the perimeter formula to help us out with that. Remember, we had that x was equal to 2400 minus 2y, right? So all we have to do now is just plug 600 into this and get the maximal value for x. So x, the maximum value of x, is going to be 2400 minus 2 times 600, which means that x equals 1200 feet. So 1200 feet for x is what gives the maximal area. So now what you could do is you could say that, remember, area was x times y, so you know the maximal area would come from just plugging this in for x and that in for y. So x is 1200, y is 600. But the problem didn't ask for the maximal area, it just asked for the maximum dimensions. So here we're done, but this is what the dimensions give you. They tell you when x is 1200 and y is 600, that gives you the maximal area. Okay, so again, the idea is no different than what we've been doing. You're just using the first derivative test to tell you whether you have a max or a min. The difficulty kind of lies in figuring out the formula for what you're working with, what you're trying to optimize, and how to turn it into just a function of one variable and proceed from there. So we'll do one more example to get a good grasp on this.